We did the energy of a mass on a spring. Let's do the energy of a mass on a string. Energy of a pendulum. All right, so let's see. So this one is very similar. We know that the total energy has to be conserved, so we would say E mechanical, whatever kinetic you have, plus whatever potential you have, you know that has to be constant. So for the mass on a spring, we just talked about those two and how the energy goes back and forth but remains constant. Another way you could write it, as we have already in the class, is delta K plus delta U equals 0. So let's look at the kind of problems we could think about. So if you have a pendulum like this, and it's going around on a curve like that, it could be up high, it could be down here, it could be up here. So in all these different places, the delta K is still related to 1/2 mv squared. And now the delta U is actually related to mgh. Right? So the potential energy that's driving this motion is related to gravity. So mg and h, or we'll call it delta y. Right? Because it's actually, the pendulum's moving up and down a little bit as you release it. So one kind of problem you could say is you release from height h, how fast at the bottom? Well, let's see. Initially, we could actually just solve it formally. We could say delta K, that's K final minus K initial. So let's call this initial and this final. Well, if you released it from rest up there, then it initially had 0 kinetic energy, and it's getting some final that you're looking for. So that would be 1/2 mv final squared, that's the final kinetic energy, minus 0, because you released it from rest. And if you wanted delta U, you're actually going down. You're losing potential energy. So you're going down to a level we could call 0. So plus the final would be 0, minus the initial would be mg delta y. Minus the initial. That has to be 0. And then you see what you would expect. You simply say you set the kinetic energy you're going to get equal to the potential energy that you lost, mg delta y. And then you go solve for whatever the problem asks you to solve for. Maybe it gave you the height and asked you to get the speed, or maybe it gave you how fast it goes and asked you how high it had to be. For this part, it's pretty much the same as sort of a ball rolling down a hill. There's not that much difference. You could even get a little more complicated and say, what's the difference? How fast is it going if you start here and you end here? Right? Well, let's see. So you can see this is a little bit further along than this. The actual point it's going to get to is a little bit higher. So we haven't come all the way down. So those problems get tricky. It turns into a bunch of sort of trigonometry and algebra. What you really need to know is these heights. So if you really wanted to think about this height, you would say, okay, I have a right triangle here, and I have it starting at some angle, and I can figure out all the properties because I know the length of the pendulum. Right? And I can figure out, if I know the length and the angle, I can figure out that this is L sine theta, because that's the opposite, and this is L cosine theta, because that's that side. And that's because it's all way up here. This side's similar. You could draw a line like that, and now we have a right triangle here, but it might be at some different angle, call it phi. Right? You know some things, you know this L, right? And if I tell you how far along it goes on this curve, you could basically approximate that curve as this height, or you could say S is theta r. But you got to think about it. It's actually these parts right here. How high does it go? This is the important part. What is this length minus L when it's hanging all the way down is the change in potential energy. And at this stage, what is this length minus L to get the heights? So for pendulum, it's a little tricky to find these heights. It's not as trivial as just seeing where it is for the spring, 1/2 kx squared. There's a little bit of geometry to figure out how high it's gone. But you can do it.